So now let me assume that we have the following graph. Okay, so V1, V2, V3, and V4. So each V represents a node here. And then we'll have some edges with directions. For example, this is my graph. So each one of these edges, we'll call this E. So E1, E2, E3, E4, E5. Okay, so here, for each one of the graph, in terms of its mathematical definition, each graph G is made of a set of V and E. So V represents the nodes here, so from V1 through V4, and E represents all of the edge sets from E1 to E5. So here, if we have a certain graph like this, what does that mean to take the Laplace on a graph? So we've noticed that here I have the gradient being a matrix. And here is also a matrix. And the dimension here, if you've taken linear algebra, this is the number of edges cross number of vertices. So in this case, if I have 5 edges and 4 vertices, this means it is a matrix of 5 by 4. Okay, so here we're going to denote all of this. So V1, V2, V3, V4. Each column, it represents a node here, and we have 5 edges here. So E1, E2, E3, E4, and E5. So in this case, the gradient on a graph means that you will be denoting each edge on its starting point and its end point. So let's assume that all of the starting point will be denoted by -1 and the end point is 1. So in this case, I can go ahead and fill out for all of the edges. So here, second edge is going from V1 to V3, and third edge from V1 to V4, and so on and so forth. So V4 from V2 to V3, and from V3 to V4. Here it should be -1 and 1. So it's actually, it's not set that is always the starting point should be -1. So as long as you fix the orientation, so if you have the rule that the starting point is always +1 and the end point being -1, that's also fine. But as long as you keep the same orientation throughout the whole matrix, that will be fine. And for the second one, we'll basically have the transpose of the gradient. Okay, so the transpose here will be from, so each column here represents an edge and each row here represents all of the incident edges of the node. So here will be 4 rows cross 5 columns. Okay, so here, let me just put in all of the entries that we have from the previous matrix. Okay, and 1 and 4. So make sure that you follow that. How did I enter all of these entries? So basically, you'll be looking at each edge and look at what is the corresponding vertices. Okay, so E4, for example, here is from V2 to V3. So we will have a -1 on V2 and +1 on V3. Similarly here for E5 is -1 on V3 and +1 on E4. Okay. So what does these things mean if you try to multiply a vector to its right? So here we have to multiply a vector of 4 entries. So assuming that we have v1, v2, v3, and v4. So after you multiply this, so this would give you, for the first entry will be v1 minus v1 plus v2. And for the second one will be minus v1 plus v3 minus v1 plus v4 and minus v2 plus v3 minus v3 plus v4. So what this means is that if you focus on each one of the entry here, we have 5 entries in total. That represents the 5 edges here. So if you put a cut, say you put something here, so this tells you that what is the direction that this edge is. So what is the, in other words, like what is the gradient of this edge? So it's floating from v1 to v2. So you have a gradient that goes from, so basically v2 minus v1. What is the difference between the two? So similarly here for each one of the edge, you put a cut here and you look at what is the gradient. Okay. So this is in physics world, this is the gradient of the graph. And now let's see what's going on with the gradient transpose. So for here, we are going to multiply a vector of dimension 5. So here E1, E2, E3, E4, and E5. So what this means is that you're going to have negative E1 minus E2 minus E3. Okay, so for the first entry, if you multiply these two. And for the second one, you're going to have E1 plus E1 minus E4. And the third one will be E2 plus E4 minus E5. And the last one will be E3 plus E5. So what this means is that if you look at each one of the entry here, it focuses on each node here. So if you look at the first entry, that would be the divergence of this single node V1 going to other nodes. So it's going to its adjacent nodes V2, V3, and V4. So all of these are negative because you are going out from V1. So if you focus on, for example, 2, and we see that there is one edge that's going into V2, that's from V1, so that's why it's positive. And there is also one edge that's going out to, there is one edge that's E1, and there's another edge that's going out, that's E4. So you have the corresponding signs to this vertices. So the previous one is focusing on each edge, what is its gradient. And the second one is focusing on each node, what is the divergence of each node. Okay, so as you can see that for each graph, we basically have 2 dimensions, one for node, one for edge. And this one takes the derivatives on the edge, and this one takes the derivative on the node. So if we put these two together, this is what we call the divergence, remember? And the other one is gradients. So if you have divergence applying to the gradient, this is basically what we said before, the Laplace operator. So this is called the discrete Laplace operator on graphs. So the idea is that you take the derivative on both dimension, and then when you put this together, basically the product of these two matrices, and you get a matrix that represents the Laplace operator, which is a matrix of V by V, right? So that would be the graph Laplacian, which you will see on the next slide. Okay, so let's move on with this idea.